Hey, so I'm aware this video is very long. I tried to trim it down as much as I could, but I could only get to 30 minutes. I want to be as thorough within this walkthrough as I could be, so I've gotten a little bit more in depth in things that you necessarily need to know in this video. So I don't expect you to take notes on this or anything. You can just view this at your leisure and refer back to it if you get stuck during the lab. But this software can be a very powerful tool for building your chemical intuition. I'm going to provide some examples of some projects that I did just because I couldn't find a good source on it. They're not necessarily complicated projects, but they're things that there weren't answers for out there, and they were very simple to solve with this software. So I'm hoping that if you want to use this software for your own purposes, that this video can be a source for that as well. Hello, so now I'm going to teach you how to actually use the GaussView software for this lab. So you're going to be using this Discovery Interactive Session window. You should be provided a link, or if not, just ask me and I can give it to you. Log it into your Northeastern account, go up to Interactive Apps, down to Gaussian, and this will hit launch, and this will just give it a couple minutes and then you'll get this, right? And then this will open up this window, and now you are running GaussView on a computer out in Western Mass. Congrats. So let's talk about what's going on here. You have two windows when you start up. I just closed out of the tips window. That's not important. So these two windows, this is kind of your builder window, and this is kind of your canvas window, or like a palette, a canvas. I want to think about it like that. For these optimizations, you remember you have to give Gaussian kind of like a description of the molecule that you're giving that has all of the coordinates of all the atoms, the charge, the multiplicity. So this is kind of the visual representation of that file you're building. So it's not just a bunch of numbers on a screen. So basically, this builder window lets you do a couple things. First, most importantly, it gives you things to copy and paste onto your molecule builder window. So you've got all these elements. You can click fluorine, get just like a fluorine atom. If that's what you want, or it usually will come preloaded with the element in just common bonding patterns to just dummy atoms like hydrogen or something. So for example, if you want to put in carbon, carbon's usually tetravalent, so it automatically goes to this one, and you click it, and it pastes a methane molecule onto your file. Hello, I forgot to note this, so I'm just going to put in this clip beforehand. When you open up your GaussView and you have your canvas here, you can manipulate the viewing by a couple different ways. You can hold down left click and drag around. You can also scroll to zoom in and out, and then you can also hold shift and then hold left click and move that around if you just want like a translate. If you need to recenter things, you have this center molecule in view. And so of course there are other things you can do. You're not limited to just how it's presented to you. Don't worry about those. Those are other things you can copy and paste down there. You can also modify all these bonds. You can actually I'll show you one at a time how to do this. So you can modify these bonds. Click on these two, and then you're given this little window. See, you can change the bond type, double bond, triple bond, whatever you want. It is worth, and also the distance. This is mostly useful for just like manipulating distances between atoms, because Gaussian doesn't actually care about what this bond looks like. If it's like a triple bond, it's only going to be calculating how many electrons are there, and it's going to place them where it's needed. So This is helpful for visual representations, so you can show this to a fellow human, but it's most important that you just, the only important information out of this is how it's changing the coordinates. Oh yeah, if you want to apply, you have to hit OK. You can't just X out of it, or else it'll just lose the changes you just did. And so next up on this list is the modify angle. This one also pretty intuitive. It'll just modify this angle of 3 atoms that you give it. Now I have 3 contiguous atoms, so that's very easy to understand, but you can actually really do anything, or really do the angle between any 3 atoms located on your molecule. Like maybe we just have 3 methanes in space right there, and then I just do that, for example. It's a meaningless angle, but sometimes something like this can be helpful for changing your molecule, because you can't just mold stuff, so it's helpful to have tools that you can think of and get creative with for trying to make your molecule look like how you think it looks like. Also, so when you have this clipboard, you'll notice that one of them is highlighted. You can change which one of those is highlighted. That's basically the atom that's going to be placed down wherever you click, which seems kind of trivial, but you can place these fragments in place of atoms on your file, or I'm just going to call this the canvas. Yeah, you can place atoms. You can place fragments in place of atoms on your canvas. So, say since I have that hydrogen highlighted, when I click that, it will place this fragment in place of that hydrogen with that hydrogen where that hydrogen was, if that makes sense. You want to play around with that, like you can also do, if you hold on to the carbon, then you'll just put a carbon right there. You'll note that this hydrogen actually disappears because it just becomes this bond right here. If you're concerned if you accidentally created an extra atom somewhere, just count the atoms that you have. It has this number right there. Let's say there was like a hydrogen that for some reason didn't get deleted properly, that was kind of in this carbon by accident. It would have a 9 right there, so I'll know, okay, something's up. If something like that happens, just come to me, I can help you fix it. Then we have modified dihedral. Actually, right here we are. So a dihedral angle is just like a 1, 2, 3, 4. This angle. See, right here. It's this angle from this to that. So right now it should be 180 degrees. Let's see if that's true. 179.8. Close enough. So as you notice that only atoms 1 and 4 are described right here, because 2 and 3 will be left alone, and it will just be changing the angle between 1 and 4 through 2 and 3, if that makes sense. I can just show you. So right now we have 2 rotate atoms, and see, now that I'm decreasing it, it will go down, cross over, and then of course, if you don't want to open that window, you just want to check something about your molecule, and just measurement, you got this inquire tool, and that is, you just click on your molecule and it'll give you information. All right, so that's just hydrogen 6. They number all the atoms in here, but yeah, unimportant. Then I click on the carbon, then I'll say H6 to carbon 5, because the 6th atom and the 5th atom, I describe what atom it is. The bond is 1.07 angstroms. Okay, that's useful. Now let's click on this carbon. Okay, so now it's H6 to C5 to C1. This angle right here, and it is 109.4 degrees. Okay, I'm going to jot that down. Now click on this final hydrogen right here. Oh, this dihedral, D for dihedral, H6 to C5 to C1 to H2, 179.8. Yeah, so you need to record that, but you don't want to open up that window. That's what this inquire tool is for. And then next you have this delete atom tool in case you make a mistake, or just maybe something in the fragment that you pasted just isn't what you want it to be there. You can just click on that and it'll delete the atom and all of its bonds. If you didn't want to do that, there's of course Control Z or Edit Undo, or I believe there's one more way of going to that. Yes, then there's an undo and redo button right there. That's important to know. This, in case you freak out, do something by accident, you can normally go back pretty far with this undo button. There's different ways of selecting on them. Select by clicking if that's something that you like. Forget how to unselect it. It's a little annoying. Oh yeah, you can just unselect it by clicking it again. Or if you'd rather kind of like draw a box around what you want to select. Another way of selecting atoms, this brush tool, you can just kind of like hold down your mouse and hover over it, and you'll select all the ones you want to select. So if you've made some progress on your molecule, you're happy with what it looks like, you can go over to File and Save. It's better to go to the directory in your Scratch folder. By the way, directory says another word for folder, if that's easier to think about. So you should have a you should have a / your name or your Northeastern username. If you can't find it, then you should also have a home folder. If you can't find your name in either of those folders, let me know. That's a problem. But yeah, so you want to make your life easy. This isn't as easy as like having like a desktop on your computer. You kind of have to kind of like navigate, and it's a pretty confusing way. So make sure to be descriptive. You want to give all of your calculations a folder, so we can call this Lab 6. And go in there. Then we can save our molecule. So let's call this ethane. And you don't have to worry about the extension. It'll either give it a GJF or .com, but for our purposes, we can just hit save and it'll make a GJF. That's what it shows. Okay, that's fine. If we're really proud of what it looks like and we want to just save a picture of it, but we don't want to use our screenshot tool because then I'll just kind of get a lower resolution. We want really high resolution. Well, it already remembers what folder we're in, and you can call it the same thing. That might be helpful. And then hit save, and then it'll just kind of take a screenshot, basically. It's a little bit like a high resolution screenshot, I guess. So now that you have a molecule, you are gonna want to give it the rest. You want to give Gaussian the full picture of what it needs to do, because it's kind of like if you go back to the ball on the hill. We have a ball on the hill, but Gaussian doesn't know what the forces in the world are like, so you have to describe it. And you also need to tell that you want to roll the ball down the hill, because there's a lot of different things you can do. For instance, you can just do a single point energy calculation, which would be kind of equivalent to just kind of being like, well, what's the potential energy of the ball at the top of the hill? But instead, we're going to be doing an optimization. So what this will do is it will take an energy, look at all the forces at play, and then roll it down a little by little, taking a point energy at each time until it basically can't optimize anymore. So yeah, this optimize to a minimum. Don't worry about any of that. If you want to just make sure that my screen looks like your screen, we should be okay. Okay, for all of our calculations, we are going to be using the ground state. There's some like excited state things with where the electrons are in the orbitals, but we just care about everything in its ground state. Yes, we're going to be using DFT, density functional theory. That's basically our approach to approximating all the forces at play. B3 lit, which is kind of like the exact functional or the kind of like the exact mathematical description of how to calculate all the forces. And then we're going to be changing the basis set to 631G and put a D there. So the basis set basically tells Gaussian how we're supposed to be approximating what the orbitals look like, because modeling their true shape and everything would be super expensive. So we just have these convenient mathematical approximations. 631G, D is actually pretty descriptive, but these are small molecules, so we can get away with that. Title, this won't actually change your job at all, but you do need to have something here, just any kind of string you want. That would work, whatever. Maybe, I mean, if you want to look at the log file later, it's good practice to call it something. Call it something that will help you understand what's going on. And then you also want to make sure your charge and your spin is accurate. These will kind of change how many electrons to put into this molecule. So for example, this is a neutral, so charge of 0, and there's no unpaired electrons going on here. It's a singlet spin. If you're not sure, like for the case of when you calculate oxygen, you can always do both. I mean, you'll have to make 2 separate files, but you can like do one, then the other, and then when we get to the point where we're looking at the energies of these molecules at their minimum, you can learn something about, theoretically, which one should be more stable, in the triplet state or the singlet state. That might interest you. And then in this link, make sure that it's going to be that the checkpoint file is not set to don't save. You want default name is just easiest to make. Just keep it as default name. And now this is a little bit different from what's in your lab, but I think it's always good to make sure all your changes save to your file. Hit retain, then go over, hit save, and then you just have to make a new file. It'll ask you, like, do you want to overwrite it? You're just making the same file, so it's whatever. Not as user-friendly as other things. Then go back to Gaussian calculation setup, because now we've saved our file and we want to submit. So we're just going to hit submit. Yes, submit.gjf. Go. So now it looks like nothing happened, but it's running in the background. Just be patient. If more than, I want to say, like 10 minutes passes, these aren't big calculations, then maybe something's gone wrong. Or I can help you to make sure everything's actually running. Alright, so now Gaussian's completed the job. It'll give us a .check and a .log. As you can see in the size, the .checkpoint file has a lot more information on it. The .log is really only just to read, like as like a text file, but the Gaussian will also convert it into a nice visual for you. So in case you're curious and want to go in, you can also open that if you're having trouble figuring out how to look at that file. I can help you with that, but it's not necessary for this lab. You can open it. All right, so this is what Gaussian made. Yeah, it looks pretty similar, as you can see. Yeah, I guess the way the kind of like the automatic calculation or the estimate that Gaussian did by itself was pretty close, but as you can see, let's see, 1.53 versus 1.54. Okay, maybe it wasn't so smart. Of course, this checkpoint file that we have in this window, okay, so it looks like this is just another canvas window, and you can kind of treat it as a canvas window, but this is actually an entire checkpoint file. If you're confused what you're looking at, just look up here. So ethane.check. This gives you the minimum optimization that it gave you for the geometry, but it also gives you a little bit more information about how it got there. That can sometimes be even more useful than the geometry itself. One of the things that you might want to look at with this checkpoint file, besides just the geometry, is the molecular orbitals. That would be really nice to look at, see where the electrons are in each of its orbitals. So you can go up to MO Editor. This will give you a couple things you can do. First of all, make sure the wave function is in restricted. If it's in unrestricted, you might have something that looks like that, which is just really inconvenient, and it'll pair all the electrons. If, for instance, you have a molecule with unpaired electrons, like this triplet oxygen I had calculated previously, you'll have unpaired electrons. It'll probably force you into an unrestricted wave function. You can still change this to restricted. This is really convenient. It'll pair off all the electrons that should be paired off and put them in the same orbital together, and then put these ones up there. So that already is looking a lot cleaner. But we're going to go back to methane. So these numbers over here represent the relative energy of each orbital. You can kind of think of this as how stable or how stabilizing it is to put an electron in that orbital. To build off of the ball on a hill analogy, you can think that it takes, let's say, 10 joules to move the ball up to the top of a short hill, or 20 joules to the top of a higher hill, whereas to move the ball from the top of the hill down to the bottom, it'll take -10 or -20 joules for that interaction to occur, whereas for the orbitals, it'll take like -19 Hartrees to put an electron in that orbital, or it'll take, let's see, like 0.16 Hartrees to put an electron in that orbital, if that gives a better, clear frame of reference for what the thermodynamics is going on here. So it's not important, but this is all in Hartrees if you're wondering what the units are, which is basically just a tiny amount of energy that chemists use to talk about molecular interactions. So yeah, here are all the orbitals. The most stable ones are in the bottom, and then they have them stacked in ascending order. This is the highest occupied molecular orbital, and this is where it starts getting unfavorable. And you can notice there's no electrons in there, because why would an electron want to be in there? So you can also notice that some of these numbers are pretty much identical, but maybe because of some insignificant digit way far out there that they're not showing. It says that orbital 9 is less stable than orbital 8. Well, I find that you can get a better visualization by changing the degeneracy threshold. So I think a good degeneracy threshold is usually, I want to say, like around there. Okay, so I cut that video a little bit short. I got way too in depth, but yeah, that's pretty much all you need to know for the orbital analysis. But here's the frequency analysis. Okay, so for NO and N2O, you are to be conducting a frequency analysis. So to do this, you're going to want to make sure that you have the .check file. This will have the optimized structure of the molecule that you're looking at. Make sure you are not looking at the old .com or .gjf file, as that is the outdated structure. It's not what Gaussian thinks the structure looks like, and it'll give you terrible results. Make sure with this highlighted, go up to Calculate, Calculation Setup, go down to Job Type, and change this to Frequency. Now you'll notice there's also an Opt plus Freq job type, and that can be really helpful for when you already know you have to do a frequency analysis. But for right now, what that does is that it'll do an optimization and then follow it up immediately with a frequency analysis just to save you the time, but we've already done the optimization, so now we're just going to do the frequency analysis. I left the frequency analysis out of the Preface video because I don't feel confident giving a good analogy. What you can think of it is it's just some quantum math magic, just going through a black box. When you get to quantum chemistry, they'll go over the equations of how to calculate a frequency analysis and how to calculate all the vibrational modes. But for now, you don't have to worry about it. What you can think of it as is Gaussian approximating each of these bonds as harmonic springs. If you've taken physics yet, then you'll know that you can approximate strings using a very simple equation. And a Gaussian will try to find the force constants of those springs, and it'll do so by taking into account the electronic environment that Gaussian has built while also trying to build the single point energy that it also used for the optimization. So you want to keep everything else the same, just retain it, save it as a new file name so it won't overwrite your old file. So, for example, I'm doing ethane.freq. I'm doing .gjf, that's probably what you're doing. And this one should also be pretty quick. So let's just hit submit. Okay, so just like in the optimization, you're going to have a .log and a .check file coming up. I think you're going to want the .check. I'll have more information in it. So now that you have the ethane.check, if you want to do this vibrational analysis, go down to vibrations. So the frequency column will give the energy associated with the vibrational mode in units of reciprocal centimeters. This might seem like a strange unit for energy, but it's really convenient when you're looking at what wavelengths of light absorb this frequency. And this infrared column should give you an approximate estimate to how strongly that vibrational mode absorbs, because certain vibrational transitions are disallowed. So, for instance, this one has a very low infrared absorption, so it has 0, whereas this one is probably very permittable, so it's a very high infrared. There's quite a few ways you can interact with this window. If you want to look at what the vibrational mode looks like, you have the start animation feature. When ethane, for example, absorbs light at 315 reciprocal centimeters, it does this. Or 833, it does that. And if you want something that might look more familiar, you want to look at an infrared spectrum that correlates with this, Gaussian actually prepares you this visual. So if you were to look at ethane in an IR spectrometer, you should get something that looks like this. Okay, so I promised you examples of ways that I've used this software in my own studies to help with my own chemical intuition. One of the experiments that I've conducted at my time at Northeastern is seeing how this 8-hydroxyquinoline ligand binds to copper, and versus some other very similar ligands. So by looking at the relative energies of how these ligands are in freely versus when they bind to copper, and then look at this one as well and see what the delta G of that interaction is as calculated by this software, I'm given almost an extra set of data to compare my experimental data with. So if they were to correlate, then I'll say, yeah, this is all making sense. But if they disagree with each other, then either my theoretical approach is flawed, or there's something wrong with the experimental data. So it's like a double check. Another set of data for this project that I unfortunately lost was kind of an infrared spectrum of this chelated complex, so that we would know for sure we were looking at the IR spectrum of 8-hydroxyquinoline when bound to copper. And here's something else that I'm working on my own personal machine for a group project in ChemBio is we're wondering if this drug target right over here is able to fit in a certain enzyme that might be able to help catalyze a reaction that it goes through. So in this case, the exact structure of the molecule we were putting in the proton pocket is very important because just small little distances in that protein pocket can create huge energetic differences. So we wanted high accuracy in the structure that we put in there. So we optimize it using a low-level B3 lip method, or low-level basis set with B3 lip, and we got this. And hopefully that'll give us a much truer result with how it fits in that pocket.